Hi Phil, welcome back. We're doing okay. All right, good morning. Welcome back to the best class of the day. I hope you guys are doing well, staying safe, and staying dry as this rain continues to hit our area. There's our Doppler radar. A lot of precipitation coming our way. A lot of rain working its way on up through. Check that out right there. But anyways, hopefully your internet connection's okay. A lot of people are experiencing problems with internet connection with today because the weather. Let's go to United States. Map I want actually. Let's go to map. Perfect. That's good for me. This big map here. Hopefully we can zoom in on this for a second. There's a map. Look at that map you can buy on Amazon. What happens with weather? Let's check out this one right here. So anyways, we'll talk about this a little bit more a little bit later as well. But anyways, here we are in central New York. That's us. Hanging out at home, virtually learning. Hey, Leo. Hey, Alex. Tried to get here a few minutes earlier. I didn't take attendance yet, actually, but there we are, just hanging out at home, virtually learning, and trying to figure out what the weather's going to be like. So what does a meteorologist do? They predict the weather, and how do they do it? A lot of times, the easiest pattern for them to do is to analyze the pattern of something called these winds, these westerly winds. So with these wind patterns, what happens, obviously it's going to bring this weather from the west coast over to our area. So a lot of times they predict what happens over, or they see what's happening over in Oregon or Washington. They check out this pattern, what's happened here, or what's happening over in Wyoming or so, or what's happening over in Green Bay, Wisconsin, or Michigan, and they predict what's going to happen over to our area. You'll see a lot of patterns working and forming from left to right, kind of like today. You saw the Doppler today. It's working its way up a little bit more like this, but these rains are working their way. Precipitation is working its way up from the west to the east. And that's how they predict a lot of these patterns. When we talk about acid rain or acids and bases in the next unit, we're going to analyze, so we'll talk about those winds again, and we'll talk about like the Rust Belt cities, Rust Belt areas. And within those Rust Belt areas, or like the northern portion of the United States, around a lot of lakes, a lot of development of communities happened around lake areas, and a lot of major cities are actually on like the Great Lakes, Green Bay. Think about Ohio. There's a lot of cities there. Buffalo. A lot of cities surrounding these are Chicago, big city. Green Bay's not a huge city, but there's a lot of cities. Cleveland, Ohio. You know, a lot of cities are over here. Erie, Niagara Falls. But anyways, with those cities came a lot of industry, a lot of like big pores or big things that gave off a lot of toxic fumes. And a lot of times what happens with those westerly winds is it drops debris or acid rain. So what happens? These fumes go up in the atmosphere, whatever garbage these factories give off, Detroit, Michigan. These fumes go in the atmosphere. They go into the clouds. The clouds travel with those wind patterns. And what happens, a lot of times it drops that debris in that chunk right there in the form of rain, or it drops in different forms in the Adirondacks. A lot of the lakes in the Adirondacks are acids, acidic acids, or some of them have acid debris in there from this garbage that it picks up along the way. So we'll talk about these patterns a little bit when we get to acids and bases. But why did I just go off on a little tangent for introduce today's class like that? Because I saw that pattern. Sorry to get so crazy. I saw this little pattern. You see this flow. Maybe man's foot. I don't know. I saw this pattern happening here. You can see that. It's working its way up. Start. And then it works its way up. Finish. Wish I could zoom in that more. But anyways, what's happening today? A lot of rain's going to happen throughout the duration of the day. Not a good day to go outside and go relax. But if you look at the next couple of days, check out the next few days. This is good stuff right here. Now we're getting excited. Now we're like, well, okay, I know. Okay, Mr. Brown, I see you. I see what you're talking about now. Spring is going to happen. Then you can start to go outside, take a nice little stroll down Valley View or down the Parkway, wherever you live. You can find a little route you can go on and get outside, clear your mind a little bit, get some nice sunlight, some UV. Yeah, it's coming up, guys. So we'll just hang out today. Get lost in a good book today. But the next few days, start to figure out a routine. It's a good chance to make a routine for like a workout pattern. Workout every day. Fit into your schedule. What time do you go for a walk, a jog, a run, whatever you want to do. Bike. Call your friend up. Say, hey, do you want to take a walk today? Get outside. I'll wear a mask if you wear a mask. Talk about all that stuff. You can talk about chemistry, all that good stuff. But better weather's on the way. Awesome. Let's figure out who the heck's here now. Alex is here, and so is Leo. So we're all here. Thanks again for coming on time for those that did. Those late, please come a few minutes early. All right, let's check out the COVID report for today. Here we go. Oneida County COVID report. Back at it. 452 cases of COVID in the county. 19,122 resolved cases in the county. And 403 deaths. We added another death to the total. Sad. Someone else and their family was affected by COVID. You can check out the hospitalization numbers, check out the vaccine numbers, but let's just check out the number of daily positive cases. The 16th, last data that was in here, we have 34 cases, day before 37, day before 20. Hopefully we stay steady. Hopefully we stay steady with those values or decrease. I don't want us up here. I don't want to go up there again. That was a nightmare. But there's the COVID report for today. Yeah, you're right for that. Definitely right for that. Moving on forward, let's figure out what's happened for the awesome class, best class of the day, chem class. Let's see the agenda for today. So again, a couple of things on here. I added a couple of announcements on here. I know you guys aren't seniors, but maybe your brother or sister's a senior and they're graduating this year. If they're graduating, there's an announcement for cap and gown for that. Maybe you can relate that to them in case they don't get the information from a different class. It's there. You can order some Proctor swag if you'd like to. It's there. A lot of assignments are coming up, but the first assignment we're working away from for our classroom pages today, our agendas today, on up. So progresses on up. We have the PowerPoint. I did put that on there for you, Santino. If you want to copy and paste those notes on there, you can put your notes in. If you want to do that ahead of time, you can check that out. Additionally, I have the textbook on here as well. 2 different chapters from the textbook you could check out for oxidation reduction. The second portion, electrochemistry, is actually topic 4, topic 5. But this textbook is available for you. You could obviously go through, you could read through it if you want more information about this class, you want to get more in depth about a topic, or maybe you just want a different view on a topic. This is here for you. Again, I am not giving you assignments within the text, but this is an additional resource. If you get stuck with something, you could always have it read the text or it'll read it to you. This is always like a big thing. We drive down the parkway with my kids, like, ah, Daddy, the big Statue of Liberty. I'm like, yes, Statue of Liberty on the parkway. It's there. It's a little bit more teal than this image is. If you ever notice that? If you look by the parkway, you can check it out. There's a small replica of the Statue of Liberty. Why did it tarnish? You want to look more about that. But again, this textbook has a lot of information there for you. It will read the information to you if you want it to. It's not a bad idea to read it yourself as well. Oxidation and reduction reactions gives you a lot of info on this topic. Talking about shift, deal, all this stuff. Gives you a lot of images here too. You can always do the questions if you want to analyze more practice questions, but I'm not signing in that yet. Cool stuff. All right, so that's available for you to read if you want to as well. Moving on forward, let's check out what else we have up here. Examples, warm up, all that stuff we'll be going through today's class. Welcome back. Best class of the day. Hope you guys are doing well. Quote of the week comes from Ralph Martson. What you can do today can improve all of your tomorrows, all your tomorrows. What you do today can improve all your tomorrows. Today's Thursday, March 18th, 2021. Today's a day 2. I will not see you tomorrow. You guys have day 3. You have phys ed, you have ROTC, whatever it may be, or study on. Unit 8, oxidation and reduction. We're going to continue on with oxidation numbers, topic 1. It's a huge class today. It's an essential class. That's going to be a foundation class for the rest of the unit. So try your best to engage in today's class. I know it's gloomy, it's tough, a lot of content today, but try your best when we get to the notes to really get in and try to memorize these rules. We're going to start with a warm-up. We'll get into the notes, and I'm not going to do 3 or 4 today. Those examples, a lot of examples will come next time. Once we have the notes down, once we start to memorize those rules for oxidation numbers, rules are over here for oxidation numbers, you'll be able to go through several examples. This unit is sometimes, depending on the people that I'm dealing with, depending on the student, for some students, this will be the toughest unit of the year. Why? Because they do not memorize the oxidation number rules. These rules over here, they don't memorize. If you memorize these rules, you do what I ask you to do for memorizing these rules, then this will be an easy unit for you. So here we go. Let's start off with a warm-up. Warm-up activities from 3/18/21. It's on oxidation and reduction. Please click on warm-up for today. A lot of these questions are basic intro questions to oxidation and reduction. Other questions are from Lewis dot diagrams, the flow of electrons. So I'm going to give you 10 minutes to work on this warm-up for today. I'll put you in breakout rooms at 12. 12:05, we'll break out the breakout rooms, we'll go over it, and we'll move on to the next portion of class. Please work on this warm-up for today, oxidation and reduction. You probably want the reference table to assist you, or even your notes to assist you with this process. So again, please join your breakout room. Please complete this assessment at 12:06. We'll break out of it and go over these questions. Please join your breakout room. If you have questions, ask for help. Give it a shot. Please join your breakout room. Please complete the warm-up for today. If you have questions, ask for help, please. Please join the breakout room. Please work on this warm-up for today. Hey, Joey, please join your breakout room. Please attempt these questions. 12:06, I will go over these questions. Okay, everybody should be back from their breakout room. Hopefully you had a chance to go through those questions, 10 questions. A lot of these questions were reviewed from the Lewis dot diagram unit, so electron configuration unit early in the year, or even bonding unit as well. So let's see what we remember from earlier in the year. Let's see how we did here. Let's go through these questions right now. So question number 1 says, what is the correct Lewis electron dot structure for the compound of magnesium fluoride? Please record your answer in the chat so we can go through it. We have 28 people in class right now. I'll wait for at least 6 responses. Then we'll get rolling. So please record your answer in the chat. Question number 1. Let's see how we did. All right, thank you. We have several answers here, A, B, and a few C's as responses. Let's check this out. Magnesium fluoride. So analyzing this equation, magnesium fluoride. Think about it. Magnesium is definitely going to be Mg. Definitely Mg there. Fluoride has to be fluorine. Fluorine. Fluoride. Fluoride. Fluorine. Fluorine. Fluoride. That's what we did. All right. Definitely. Fluoride's got to be fluorine. We know that. So the first step is we know the symbols are going to be Mg and F. Mg and F. All right. Can't get rid of anything there. The charges. No, let's not do the charges yet. Let's do the Lewis dot diagram first. Let's do the Lewis dot diagram for Mg, which in Mg would have 2 dots, 1, 2. And let's check out the Lewis dot diagram for F, which would have 7 dots. 1, 2, 3, 4, 5, 6, 7. Should have done the charges first. So anyways, what's going to happen here in the situation, Mg is going to give off 1 electron right there. It's going to transfer on over. That'd make a stable octet within this F. And then you realize there's another valence electron there. It has to go somewhere else. It's going to go to another F as well. So I probably should have went with the charges first, but I didn't. So this F has 7 dots. 1, 2, 3, 4, 5, 6, 7. That other valence electron that Mg has is going to transfer on over to here. So that's going to transfer on over from there to there. My first step should have been to figure out the charges for Mg and F. Mg has a charge of +2. And F has a charge of -1. And then I would have sent Joseph a message that, Joseph, what do you do now? You take the 2 charges and you cross them on up. Take the 2 charges, cross them on up. Take the absolute value and cross the charges. And then you would say, hey, the formula is Mg 1 F 2. There's got to be 2 F's. So if there's not 2 F's, that cannot be correct. You took the 2 charges and you crossed them on up to get the formula. Mg1 F2. So once you took that, then you could have came up with the correct formula or Lewis dot diagram. So Mg F2, let's analyze that one again. What happened in the situation? We transfer the electrons. You saw the transfer of electrons. And once you transfer those electrons on over, I'm missing an electron on the F to the right. Pop that in. I know it's kind of tough to see there, but you have F that gained an electron. Since it gained an electron, its charge is going to be -1. -1. this F to the right gained a pink electron. That charge is going to be -1 as well. What happened to the Mg? Mg lost the electrons. It lost the electrons. It has a charge of +2. You saw it lost 2 electrons. You put brackets around this as well. So why is there brackets around it and why are the charges represented? Because it's an ionic bond. You have a metal and a non-metal bonding together, transferring electrons. You need brackets, you need a charge. Negative charge has 8 dots around it. Positive charge have no dots around it. The best answer is choice C. The best answer is C. Best answer for number 1 is C. Hopefully you guys remember that stuff from earlier in the year. Number 2, it says, which Lewis electron dot diagram is correct for S-2 ion? What's the best answer for number 2? Please put the answer in the chat. That one's a little easier. Now we're bringing it back. Bring this information back out. S-2. That one. S-2. Thank you. A lot of D's, a few C's. A few C's as well. So let's check it out again. S, we know sulfur. That represents the protons, the neutrons, and the non-valence electrons. S has 6 valence electrons. 1, 2, 3, 4, 5, 6. This would be the Lewis dot diagram for an atom of sulfur. It wants the ion for sulfur. So sulfur's ion, you need brackets. You need the charge, -2, 2 minus, either way. And now think about that process. What does that -2 mean? Doesn't mean you take 2 away, but you do the opposite of what it says. You actually add 2 more electrons. If I add 2 more electrons to the last shell, that would equal 8. So we have to add 2 more dots. So 2 more dots, 1, 2. You add 2 more dots, it's going to be a -2 charge. Take 2 more dots, take 2 more electrons on. You grab 2 electrons out of there, it's going to be -2. Best answer here is choice D. Number 2, the best answer is D. Next up, nice job. Most of you guys got that one right. Number 3, talking about redox reactions, which we didn't talk about redox yet. It'll be the next portion of notes. Our redox reaction is going to be dealing with oxidation and reduction. Something's going to lose electrons and something's going to gain electrons. This best answer is going to be choice C. Probably didn't know that one yet. Maybe could have inferred about that, but C is the best answer for number 3. Number 4, next up, what occurs when an atom is oxidized in a chemical reaction? Should be able to do that one. Oxidized, which one is oxidation? Please put the answer in the chat. Something's oxidized, what happens? Number 4, best answer. So I know you know this phrase, oxidation. Oxidation, you see oxidation, I think the phrase about Leo. Loss of electrons is oxidation. Oxidation, oxidize, oxidation. So it's got to lose electrons, loss of electrons, oxidation, loss of electrons. It's got to be A or B. And think about it, electrons are negative. If you take an electron off of an atom and throw it away, you take a negative charge off an atom and get rid of it, it becomes more positive. You lose an electron, the oxidation number is going to, which many of you guys picked. Nice job, thank you. It's going to increase in oxidation number. 4, best answer is going to be choice B. 4 is B, lost electrons and increase in oxidation number. 4 is B. Check it out again in the reference table. Elements that lose electrons are going to be metals. So these metals here, several metals, these guys like to lose electrons. Why? Because it's a heck of a lot easier to get rid of 1 electron to get to the stable like that. It's a heck of a lot easier to get rid of 1 electron rather than to gain 7 electrons. It takes a lot more energy to gain 7 electrons rather than to lose 1. It's going to take the easier route. There's 7 green arrows going in. There's 1 pink one going out. Which one's going to be easier? Definitely the pink one. So if you lost that 1 electron, that negative charge is now gone. What's remaining? It's going to be a positive charge. Or in this situation, if you lost 2 electrons, get rid of 2 electrons, what's the overall charge? +2. This one, if you get rid of 3 electrons, those 2 plus 1 here, that'll give you a stable octet. So that turned into 8. You got rid of 3 electrons. What's the overall charge? A +3. You lose electrons, the oxidation number increases, become a positive. Best answer for number 4. Best answer is going to be choice B. Number 5. What occurs when a substance in an oxidation reduction reaction is reduced? Reduced refers to reduction. Reduced, reduction. What's the best answer for 5? 5. Grrr. Grrr. Sorry, I get a little violent sometimes around here. Get a little lonely and violent at school, so I start growling. Grrr. Grrr. Reduced is reduction. Gain of electrons, reduction. Gain of electrons, it's got to be reduction. It's got to be C or D. Gain of electrons. If you gain electron, take a negative charge and add it onto an atom. Take 1, take 2. Add 2 electrons on. Take 2 negative charges, add them on. The oxidation number is going to decrease. Few put that answer. Gain of electrons. Oxidation number is going to get smaller. It's going to decrease. Think of an atom that would gain electrons. The best answer is C. Let's think about that a little bit more. Think of an atom that would gain electrons easily. This likes to lose. Metals like to lose, becomes positive. But if we look at the other side of the table, like non-metals, this guy has 7 electrons, has a high electronegativity. It wants to gain 1 more electron very easily. Electronegativity is the attraction for electrons. So things with high electronegativity gain electrons easily. This has 7. It only needs 1 more electron to make a stable octet. If I add 1 more electron in, zoop, comes on in, I take the negative charge, add it on, this overall charge of this ion would be a negative. So the oxidation number is going to get smaller, negative, in that situation. So 5, best answer is C. 5 is C. Number 6, tricky question. Question reads, if the electron dot structure for X and X, which element could X represent? Let's give you that Lewis dot diagram for 2 X's. What could X be? Please put the answer in the chat. Try your best. Yes, Zen, thank you. Yes, Faith, thank you. Yes, Tintin, good. In my other 2 classes, no one could even get this one right. No one even remembered how to do it, but it's okay. It's not a big deal. It's not like you have a Regents at the end of the year now, but you do have a final. Regardless, you still have a final. All right, so a lot of you guys picked D, maybe a C in there as well. So let's check it out. So if I'm analyzing this question, the first thing I would do is check out how many electron totals are in this equation or this Lewis dot diagram. How many dots do we have there? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I have 14 total electrons, 14 electrons. How many atoms do I have? I have 1, 2. I have 2 atoms. How many electrons are around each atom? Just divide by 2. You'd figure out that each atom has 7 valence electrons. So this X is going to have 7 electrons. This X is going to have 7 electrons as well. Which one has 7 valence electrons? You can go through, and you can notice that chlorine is going to have 7 valence electrons. That'd work out. So that would be like Cl and Cl. Each have 7 dots around it, and they both need one more, 7, 8. One more electron. That one more electron they need has to go right in the middle with the remaining 6 electrons around it. 7 electrons around that first chlorine. The other chlorine is going to have 7 around it as well. 7 plus 1 is 8. That one more electron you need goes right in the middle. So 1, 2, 3, 4, 5, 6, 7. Again, this would be a single covalent bond. 7 electrons, 7 electrons. That looks like it's similar. Choice D is going to be the right answer. Let's check out for review N. N2. If there's 2 nitrogens. We talk about nitrogen had 5 valence electrons. I have 2 nitrogens hanging out. Each nitrogen has 5 valence electrons. To get to a stable octet, it needs 6, 7, 8. The 3 more electrons you need has to go right in the middle. 1, 2, 3. There's 3. And then it has 5 total. Or 5. 5. Okay, we see that connection. This nitrogen to the right has 5 electrons. It needs 6, 7, 8. It needs 3 more electrons. Those 3 more electrons you need has to go right in the middle. 3, 4, 5. This would create a triple covalent bond. Sharing electrons evenly. This would be a non-polar. No pole of electrons. They're sharing them, just like 2 twins would share these electrons evenly. They're symmetrical. Non-polar covalent bond. Hopefully you remember that term. If not, we'll talk about it later throughout the year. And O, oxygen, 2 O's hanging out, bonded together. Oxygen and oxygen. Each oxygen has 6 valence electrons. So this oxygen, number 1, is going to have 6 dots. It needs 2 more to make a stable octet. 6, 7, 8. 2 more electrons you need, go right in the middle. And there has to be 6 total dots around the oxygen. The other oxygen, oxygen number 2, has 6 valence electrons. It needs 7, 8. Those 2 more dots you need go right in the middle. 2, 4, 6. Should be a little tighter, closer, but it's not. This would create a double covalent bond. Again, sharing electrons. It's a non-polar covalent bond. It is symmetrical, cut in half, same thing on both sides. They're sharing electrons evenly. And last up, the H. 2 H's, not on the screen, but H has 1 valence electron, the other H has 1 valence electron. This is stable. It's not a stable octet because there's not 8, but stable because the first ring of an atom, or the nucleus, first ring has a maximum of 2 electrons. Every other ring, the maximum number of electrons or the stable octet is going to be 8. After that, talk about the stuff. How do you know where to put the dots for which one? Or all of them? Someone asked, how do you know where to put the dots? Yeah, double bonds, triple bonds are trickier. Double bonds, triple bonds take a little bit more practice for where you put the dots. I analyzed nitrogen. When I talked about nitrogen, I said nitrogen had 5 valence electrons. And think about it. It needs to get a stable octet. Octet means 8. It wants to be like the noble gases, which is not my screen. It wants to be like noble gases to get to 8. 5 plus what gives you 8? 5, 6, 7, 8. 5 plus 3 gives you 8. Those 3 more electrons that you need had to go in the middle. That's the first step I did. The first electrons you need has to go in the middle. 1, 2, 3. But nitrogen has originally 5 electrons, so there's 3 there. I need 2 more electrons around that first nitrogen. this other nitrogen right here, same number of valence electrons. There has to be 5 dots total around it. It needs 6, 7, 8. It needs 3 more dots, electrons, to get to the stable octet. Those 3 more electrons you need has to go in the middle. So that's why we place those in the middle. Double bonds, triple bonds, they're a little trickier. You may want to check out the covalent bonding nonpolar lesson from probably around mid-December. Back in the notes to check that out. So that created a triple covalent bond. They're sharing the electrons there in the middle. So those are a little trickier. I'm not going to go through too much more of that. If you need more help, I'll definitely help you out with that. That's a triple covalent bond. Sharing electrons, my red, I know it's getting a little messed up here. Everything in red is just sharing electrons. 2, 4, 6, 8. That's 8 electrons total. We're on the first N. I know the second one, orange, 2, 4, 6, 8. 8 electrons are on the second one. We'll review more of that stuff a little bit later when we get to the end of the year, just to overview it again, see it again, all that stuff. Best answer here is going to be choice D. Let's move on forward, though. Number 7, X, with 2 dots around it, represents what? Please put the answer in the chat. Yes, Alex, that's in. Thank you, Faith. Tintin, yes, thank you. So groups of the periodic table, you guys memorize the names of the group. Awesome. So different groups of the periodic table, we have alkali metals, which is group 1. Group 1 has 1 valence electron, has a charge of +1. They want to lose electrons. Alkali metals is group 1, pink. Group 2 is called alkaline earth metals. Earth metals, group 2, they're metals. They have 2 valence electrons. 2 valence electrons. Looks like that's the best answer. Next group up here is halogens. It's called group number 17. This is a group that has all 3 phases of matter existing at STP. You have gases, you have the liquid, bromine, and then solids are on the bottom. This group has 7 valence electrons, typically a charge of -1. And transition elements, the big chunk in the middle, group 3 to group 12. The number of valence electrons vary. Could be 18 valence electrons, could be 1, could be 2. The number of valence electrons vary. That's not a characteristic for transition metals. Best answer here is going to be choice B. Number 8, moving on forward. Given the Lewis electron dot diagram, which electrons are represented by all of the dots? The dots here represent what? Please put the answer in the chat. Cool. Carbon and hydrogen valence electrons. The valence electrons are responsible for bonding. The valence electrons are what we represent in the Lewis dot diagram. Valence electrons. That's methane. Well, we're getting closer to identify what that is, how to identify that. That is choice C for number 8. Number 9. Probably the toughest question here. Toughest question on this assessment. Which Lewis dot diagram represents CO2? CO2, carbon dioxide. Cool, some of you guys got this one right. CO2. So I'm pulling up my notes from way back in the day. Chemical bonding. Talked about a lot of stuff in chemical bonding unit. 30 pages, that's a long unit. So if you need more help with like identifying valence electrons, you can pull out your notes and hopefully this will help you with that a little bit. Maybe you can find the video to help you out. Maybe you want to practice some more of those. It should match up to something like that. There's CO2. Did that back in the day. We copied it on down. Carbon dioxide. We should be able to notice that carbon has 4 valence electrons. There's 1 carbon. So 1 carbon and 2 oxygens, 2 O's. We can't get rid of anything there. Every answer has 1 carbon, 2 O's up there. So can't get rid of anything yet. My carbon, the first carbon, has 4 valence electrons. So there's got to be 4 electrons in this carbon. What's going to happen? There's going to be 2 on the left. There's going to be 2 on the right. And it has 4. It needs 5, 6, 7, 8. It needs 4 more electrons. Where is it going to get the other 4 electrons from? It has to get 2 from this guy. It's got to get 2 from this other element as well. Let's think about oxygen for a minute. Let's rewind for a second. Let's look at O. Okay. Oxygen has 6 valence electrons. I know it's probably small on your screen. Oxygen has 6 valence electrons. It needs 7, 8. It needs 2 more electrons. 6, 7, 8. It needs 2 more electrons. The 2 more electrons that you need has to go in the middle. So you're starting off always 6 electrons. It needs 7, 8. The 2 more you need that has to go in the middle. It's going to share them that way. And then oxygen is going to have 6 total electrons. I don't care where these other 4 go. Not a big deal. This oxygen to the right, oxygen number 2 we'll call this, has 6 valence electrons. It needs 7, 8. It needs 2 more electrons. Then I don't care where the remaining 4 go. Just has to be 6 around it total. If you look at that diagram, you have 6 here, 6 here, and then you figure out carbon has 4, then hopefully you can figure out it's going to be a double bond on both sides. So that is probably the trickiest question for double bonds that you would even see. That's carbon dioxide. Carbon dioxide, choice C, best answer. Number 9, best answer C. Tough question there. Last question right here, finishing up, calcium oxide. Which equation represents calcium oxide? Please put the answer in the chat. Thank you for all your responses. I appreciate it. Definitely makes I analyze these questions a little bit easier for me to know what you guys know, what you don't know. Calcium oxide, thank you for your responses. A lot of the same answers. Choice D looks very familiar. Calcium is going to be Ca. We know that. Easy. Calcium Ca. It is in group 2 of the periodic table. Group 2. So it's +2 charge. Oxygen is oxide, charge is -2. Then I'd say, hey, what's the formula? You could cross those charges to get the formula. We have Ca2, O, absolute 2. Take the absolute value. That's a formula. None of these up here match up with Ca2O2. So hopefully you figure out that's a molecular formula. We're going to have to simplify. There's a common term. Common term's 2. 2 divided by 2 is 1. 2 divided by 2 is 1. All right, so we need Ca1O1. Oh, they're all Ca 1-to-1 ratio. Didn't help us out at all. But anyways, after you did that formula, you'd figure out Ca1O1. Then you could go back to the charges. Ca and O. How many valence electrons are in Ca? Ca has 2 valence electrons, 2 dots. How many valence electrons are in O? O has 6 dots. 1, 2, 3, 4, 5, 6. You could see what happens to make a stable octet. What's easier? What's the easiest route that's going to happen here? Calcium is going to have to donate some electrons. It's going to transfer. This electron's going to jump in right here. This electron's going to jump in right here. Think about that process. What just happened there? What happened? is they transferred their electrons. When calcium transferred 2 electrons, it lost them. It lost electrons, creating a charge of +2. It loses 2 electrons. These 2 electrons are now gone. The charge is now going to be +2. Throw some brackets in there as well. What happened when oxygen gained those 2 electrons? 1, 2. As it gains 2 electrons, it gets a charge of -2. That's where the charge of -2 comes from for oxygen. And this idea of gaining and losing electrons, like an ionic bond, is like a fundamental of what's happening in this unit. That's why I added those questions. That's why I kept asking more and more questions about ionic bonding, transfer of electrons here. So 2 more electrons there. We need brackets. Brackets. You don't need brackets around the positive charge. I like to put them just to say, hey, they're there as well. No big deal. So this last answer, question number 10, the best answer is going to be choice D. Transfer of electrons, you can figure out which one lost, which one gained. You know which one's oxidized, you know which one's reduction, GR. You could see that all within the expression. All right, that warm-up took some time, no big deal, because I wanted you guys to see those questions again and get familiar with them, because it's going to help you out with the rest of this unit. So this assignment, you can submit it. You don't have to. I'm not grading it. It's more a review to move us on forward to jumpstart our guided notes. Please open up your guided notes on oxidation and reduction. Your file, you should have like all your documents in there. Hopefully you guys are starting to organize your files, because you probably have other classes with Google Docs on here as well. So hopefully you can organize your files with like all Regis Chemistry guided notes. That'll be a pretty cool file at the end of the year. Wow. So by the end of the year, if you like put all this stuff in a certain file, my file looks like this. My drive. So maybe instead of like having like units like this for chemistry class, maybe you just have Regis Chemistry, maybe you have AP Euro, whatever math classes you're in. But then once you click on your file for Regis Chemistry, you'll have like units 1 through units 11 at the end of the year. And that'll be a nice accomplishment, I think. It'd be cool to have it all together. All right, but anyways, here we go, back at it. Topic number 1, assigning oxidation numbers. We talked about oxidation, we talked about reduction. We analyzed the transfer of electrons when we burnt magnesium. Let's move on forward. Not a ton of time left for notes. So here we go. What's going on in this unit? We're analyzing something called redox reactions. Again, I'm going to highlight my cap block. I'm going to bold. Add all that to my notes for today. So redox reactions are going to be reduction and oxidation. All it is. So my title of the unit is oxidation and reduction. A redox reaction is when you have oxidation and reduction occurring. You can see that there, redox, reduction, and oxidation. So this chemical reaction is like if you walk down Genesee Street and drop $100, or you lose $100 down Genesee Street. Genesee Street usually is pretty populated. Someone's probably going to find that $100 eventually. They're probably going to try to return it back to you. If not, they're probably going to spend it on whatever. So a redox reaction, what is a redox reaction? It's when something loses electrons, Leo, and then something's going to have to gain those electrons as well. You can't have one without the other. If you lose electrons, something's going to have to gain them. You lose electrons, something's going to have to gain them. Leo says grr. Leo says grr. Always. Something's lost, someone's going to gain it. In a redox reaction, so I will say redox reaction, and you'll know oxidation, reduction. Reduction, oxidation. Redox. Unit 8, redox. You can use that as well. Just what chemists use because they're nerds sometimes to abbreviate some long phrases. When one atom loses an electron, There must be another atom available to gain the electron. Leo says Ger. I always say that phrase together. Leo says Ger for a reason. Something loses electrons, something has to gain them. To gain the electrons. Something loses electrons, something's going to gain them. You lose $100, someone's finding it. They're going to spend it. Hopefully. Hopefully it's just not gone. Well, hopefully they return it back to you. That's what I would do. Hopefully you would do the same. Do the right thing. Oxidation and reduction reactions cannot occur alone. They both must occur in a reaction. So you cannot have electrons just lost and not go anywhere. They have to go somewhere. Something is going to gain them. The term redox is a term used to express oxidation and reduction. Redox, oxidation and reduction. Something's losing electrons, something's gaining electrons. Easy. Oxidation numbers or oxidation states. We analyze these a lot throughout the year. Oxidation numbers, oxidation states. Chemists use systems that make it easier to keep track of the numbers of electrons lost or gained. So those numbers, those oxidation numbers, tell you how many electrons are lost or gained. By atoms in a reaction. So chemical reaction, you can analyze electrons lost or gained. And that's what we're really going to do. We're going to watch these little sneaky little electrons. We'll figure out which atom lost electrons, which one gained electrons. We'll figure out which one's oxidized. We'll figure out which one's reduced. We'll figure out something called a half reaction. A lot of cool stuff we're going to put together. Oxidation numbers can be positive, negative, or neutral. So positive values are going to be metals. Typically, negatives value are going to be nonmetals. Typically, or neutral, which are noble gases. These are known as oxidation numbers. And again, if we analyze, I've introduced oxidation numbers since ions. You should be aware of what they are. Changes in oxidation numbers identify electrons either gaining or losing electrons. So if there's a change in oxidation numbers, atom's neutral, but when there's a positive sign for the atom, then it means it lost electrons. Or a negative sign indicates it means it gained electrons. So changes in oxidation numbers identify how many electrons are either lost or gained by an ion. And oxidation numbers are used to identify the path
of electrons in a redox reaction. So again, we're going to figure out these electrons. We're going to figure out the flow, where these electrons go, who lost them, who gained them, how many were lost, how many were gained. So again, the path of electrons in a redox reaction. And once you're ready, we'll copy down this little phrase. We'll write the phrase down again. Leo says GER. We'll figure out the components of what this thing means as well. That phrase, again, fundamental for this unit. We'll refer back to that several times throughout the unit. That phrase. Hopefully you're ready. Again, I'm recording the class. If you need something or miss something, internet goes out. You could always rewatch this lesson too. So Leo says GER. I'm going to copy. I'm going to highlight it. I'm going to copy that phrase. I'm going to go into my drawing board, insert drawing new. We used to use this like all the time back in the day. Now I'm going to paste it on in there. You can make it larger, whatever. And I'm going to add some vertical text boxes. So I'm adding a T, the text box. I'm going to just drag it on down vertically. And in each one of these, I'm going to put the phrase, loss of electrons is oxidation. The first one, loss. After each letter, I'm pressing enter. Done with that one, make another text box, vertical text box. Loss of electrons. Is oxidation. Loss of electrons is oxidation. Leo, the lion, says grrr. He's mad. Leo says GER. You should know GER stands for the gain. Sorry if I scared you at home. Gain of electrons is reduction. Just going to copy and paste electrons. We already have it one time. Save me 20 seconds probably. Gain of electrons is reduction. We should know that phrase inside and out. Yes, the video the other day said oil rig. You can use that one. I'm always going to say Leo the lion says GER. Leo says GER. It's a little bit more intimidating, you know, than oil rig. Leo says GER. Loss of electrons, oxidation. The gain of electrons is reduction. Know that phrase. Know what it means. Once you're done with that, please save and close it. Again, you could, oh, I copied it twice. I didn't cut it. So you could cut the last one if you didn't cut it, or delete it. Don't need it there twice. You could wrap this, so you can move it around. You can move this text box wherever you want it in your notes. Leo says GER. Does anybody need help with that last drawing? Okay, I'm guessing we're okay with our time. Oxidation numbers. Oxidation numbers are written different than ionic charges. So charges and oxidation number typically have a different meaning or typically have a different setup. They both mean the same thing. Charge is typically supposed to be written plus or 2 plus, while oxidation numbers are the opposite, plus 2. I've told you from get-go, +2. I've really told you, don't worry about that. It's not a big difference between the 2 plus or the +2. I always go +2. Not a big deal, but there's a difference. Moving on forward, rules to memorize. These rules you should definitely be aware of that are essential for the rest of the unit. Rule number 1, so memorize these units or these rules. Every uncombined element has an oxidation number of 0. Atoms charge is equal to 0. So I'm going to put 2 different versions here for this one. This is the written out one. Every uncombined element has an oxidation number equal to 0. Or what I would memorize is atoms charge equals 0. So every uncombined element has an oxidation number of 0. Okay. Or if you want to memorize this, I think you guys could make this connection. Atoms charge equals 0. And atoms charge is equal to 0. Atoms oxidation number equals 0. Why? Protons and electrons cancel out. They're equal to each other. Protons and electrons cancel. For example, in this equation below, 2 NAs plus Cl2 yields 2 moles of NaCl. Yeah, this is an addition reaction. You're taking those 2 things to make one compound. But in this reaction, the reactant, Na, is by itself. It's an atom. It's uncombined. It's an atom. Or Cl is bonded with itself. That is still going to be an atom that's not bonded with anything else. The charge of Na, if there's no charge represented, it would be equal to 0. It doesn't have to be represented like that because it's already equal to 0. So anything that's an atom by itself, its charge is equal to 0. What does that really mean? It means that your protons and my electrons are equal. They both cancel. Atoms charge equals 0. Easy rule. Should be an easy one. First rule, atoms charge equals 0. Second rule, monatomic ions. So ions, monatomic ions have an oxidation number equal to its charge, which you could see it's the same exact thing written below. That's the in-depth version. I'm just going to delete the second one. Or a simplified version for this rule is ions charge equal the oxidation number. So ions have a charge to it. Why? Because they either lost or gain electrons. When ions charges are represented, that's the charge or the oxidation number. There's a charge represented, that's the oxidation number. The first example, there's no charge represented, that's an atom. That charge is equal to 0. Second situation, I have the same equation, but I have to edit this a little bit. In the equation, Na is going to have a charge of +1, so please add this in there. I would have had you put this in with a pencil or pen in class, but please put this in here. So +1 is going to be control period plus or +1. Cl's charge is going to be -1. So please add those in. When the charges are represented, say those were there for you. If they're represented, that's the oxidation number. Atoms charges are equal to 0. When the charge is represented, that's what the oxidation number is going to be equal to. Easy. The monatomic compound for Na has a charge of +1. Therefore, the oxidation number is going to be +1. Cl's charge is going to be -1. Not too hard. Next up, Rule number 3, to memorize, which is on the reference table, it's going to be about group 1. Group 1 or alkali metals. I'm just going to say have an oxidation number of +1. +1 in a compound. So when it bonds, group 1 is going to have an oxidation number of +1. Additionally, group 2, there's a rule for group 2 as well. So group 1 has an oxidation number of +1 when it's in a compound. If it's by itself, it's going to be an atom or it could be an ion. And with examples, you'll figure out what all this stuff really means. And the second part of this rule, I'm just going to copy and paste the one above. There's 2 parts of this. Control C's copy, Control V's paste. Group 2, alkaline earth metals. Alkaline earth metals have a charge of, check on the reference table, the earth metals, not my emails. Earth metals, group 2, has a charge of +2. +2. Some of you guys probably memorized that already. Group 2, +2. That means you want to lose 2 electrons when they bond in a compound. Again, if it's an atom, it's going to be different. If it's by itself, it's different. But like up here, Na, it's in a compound, fixed ratio of 2 or more elements. This situation, Na is going to have a charge, or this situation, Na is going to have a charge of +1. It's in a compound. This is an atom. It's by itself. This is an ion. It has a charge with it. Na in a compound, group 1 element, is going to have a charge of +1. If it's Mg and O, Mg to have a charge of +2. Rule number 4, next up, halogens, group number 17. They're called halogens. They have an oxidation number of -1 in a compound. There's more than one oxidation number here, but the general rule for group number 17, and it will get more complicated, so we'd have to memorize this one first before I get to the other ones. Halogens, group 17, have an oxidation number of -1. -1, the first one listed. -1, the first one listed. -1, first one listed. -1. Yeah, it could get a little cray-cray by having more than one oxidation number. And we'll get to that cray-cray moment a little bit later. We'll figure that out. Let's not get too cray-cray. Okay. All right, rule number 4, halogens are going to be -1 in a compound. That's the first charge listed. Sometimes it could be +1, +5, +7. We'll get there a little later. That's rule 4. And rule number 5, we'll get through a couple more rules and we'll call it quits here today. So far, these rules are pretty easy. If you think about it, atoms are equal to 0 charge. Ions charge equals oxidation number. We know about group 1 is going to be +1 in a compound. Group 2 is going to be +2 in a compound. Group 17 has 7 valence electrons. It wants to gain electron. That one you could probably figure out. Rule number 5 is referring to hydrogen. Maybe a little more difficult. 2 portions of hydrogen. Hydrogen in a compound. H equals +1 in a compound when it bonds with a nonmetal. When bonded with a nonmetal. Hydrogen is going to be +1 in a compound when it bonds with a nonmetal. Think about nonmetals, nonmetals, nonmetals. Top right portion of the periodic table. Nonmetals are high electronegativity. They want to gain electrons very easily. They gain them easily. Nonmetals, if they gain electrons, become negative charge. Nonmetals are negative charge. If nonmetals are negatively charged, H, which has the ability to be positive or negative, nonmetals are negative, H is going to be positive. So why? Opposites attract. Ionic bonds, opposites attract. So H is going to be positive when it's with a nonmetal, which would be negative. In the opposite situation, copy this whole thing again and paste it below. Get rid of the garbage on the bottom. Copy and paste. We'll edit it a little bit. Control C, Control V. H is going to be -1 in a compound when bonded with a metal. The metal would be, I should probably put that in there, a positive something. Non-metal would be a negative something. Let's just wrap it up with this example. In the equation with HCl, Cl is going to be negative because it's a halogen, -1. H would have to be +1. So H would be positive, Cl would be negative. It's a halogen. So H would be +1 in that situation. Those are examples. The last one, Li is in group number 1. Group 1 is going to be +1 charge. If Li is +1, H would be the opposite charge. H is going to have to be, control period brings it on up, -1 for a charge. And next class, we'll analyze a ton of these examples. We'll finish up the rest of the rules. But I did want to go slow through them. Hopefully by now you can think of the first 5 rules, memorize them. It'll make next class a lot easier. On that note, folks, that's it for this rainy day. Stay dry, stay warm. Brighter days are ahead. And stay safe. We'll see you guys next time. Enjoy the day off tomorrow. See you later, guys. Have a good day. Bye. Make good decisions. Bye, John. Bye, Jordan. Have a good day. Bye, Kai. Bye, Faith.
See you, Mr. Brown.
Take care. See you later. Oh, it's a weekend. I won't see you guys tomorrow. Enjoy your weekend. Bye, guys. See you.